Hello, and welcome to this first video in the Welding Metallurgy playlist, where we're going to review weld section analysis. To begin with, let me start by sharing the screen so you can follow the PowerPoint as we discuss the topic. My name is Girish Kelkar, and I am a welding consultant working as WJM Technologies, which stands for Welding and Joining of Materials. And today we're going to talk about metallurgical evaluation of welds. When you make a weld, you obviously want to test it for quality. One of the ways to test quality is by non-destructive means, so the sample is still intact after testing. And that can include X-ray, visual, ultrasound, dye penetrant, leak check, among others. There are some techniques where the sample eventually gets destroyed, and that is including weld strength testing, such as burst test, pull test, shear test, and can also include weld section analysis, where the sample is sectioned, polished, etched, and photographed, and in many cases also tested for micro-hardness. The photograph on the left shows a welded sample, and you can see the weld. Obviously, it's a fillet weld, and we have marked the location where we want the weld to be sectioned. We transfer the sample to the metallurgy lab, where they will section the sample and then polish it and etch it to reveal the microstructural details as shown in the photograph below. The polishing equipment is fairly straightforward. You need some way of mounting the sample that can include a Bakelite press or epoxy mounts, which I can show you on the next slide. Then the samples are polished using sandpaper and in some cases, aluminum oxide and diamond paste. Once the sample is sufficiently polished, it is etched to reveal the microstructure and photographed using a microscope. Epoxy-mounted samples, as are shown in the photo on the left, when the samples are fairly small, the epoxy mounts are of the order of 1 inch in diameter. However, in structural welds, the weld itself can be quite big. In that case, the epoxy mounts also are quite big, as you can see from the scale below. In either case, the samples have to be polished, etched, and photographed. Once the sample is etched and photographed, the lab will send you back images, and image can look something as shown in the photo on the screen. This is a resistance spot weld, and the weld has been made between the two sheets over here, and the cross-section has been taken around the diameter of the spot. And you can see 3 different zones in the photograph. You see the fusion zone, the heat-affected zone, and the base metal. Fusion zone is that volume of metal which would have reached melting point during the welding process, and then it froze. The heat-affected zone is a narrow band of material around the fusion zone, which got quite hot but did not melt. So it got hot enough to change its properties to a substantial extent, but not hot enough to melt. And that heat-affected zone can appear with a different texture in the cross-section. And then, of course, we have the base metal. So after welding, you can actually have 3 different zones: the fusion zone, heat-affected zone, base metal, which can have completely distinct mechanical and chemical behavior or properties. Here's an example of a cross-section. Again, this is a resistance weld where the 2 parts have been joined, and the junction is as shown over here, where you can see a distinct line. In this case, the 2 base metals obviously look different, so they are different types of steels in this particular situation. And you do not see a fusion zone along that interface. Now, this is quite interesting and also quite common in resistance welding, where there is no fusion at the interface. There are many other processes, including friction welding, where there is no fusion. So in this case, we have the base metal and the heat-affected zone. And the heat-affected zone over here, we can see that the flow lines can be seen of the material having been flowed during the welding process. This is a projection weld, and we will review projection welding in another video in this playlist on resistance welding. When we look at the weld, we also are interested in trying to understand the mechanical behavior of the weld. In many situations, the welds we make are very small, so it is very difficult to actually remove a certain volume of the metal for mechanical testing. So what we do is we use micro-hardness as a proxy for strength. So we ask the lab to run a micro-hardness scan. A micro-hardness, as the name implies, is a very small diamond indenter to test the hardness in a certain location. The indent looks very small. You can see the length over here is 100 microns. And we can make these indents from base metal on one side to the base metal on the other side. In this particular image, I'm showing you locations where the hardness would have been taken, but these are all only schematics. The actual indent would have been very, very small. So obvious, sometimes not evident at this magnification. What we are interested in finding out if certain zones in the weld have become very soft or very hard compared to the base metal. And it can be both. The fusion zone can be harder or softer, or sometimes even the heat affected zone can become harder or softer compared to the base metal. How does it affect welding? A zone, in any zone, which is much harder than the other, is more susceptible to crack growth. So let's say in this case, this is the fusion zone, and let's say the fusion zone ends up being harder than normal or compared to the base metal. Now this weld is a butt weld where the two parts have been pushed together and made a weld. And you can see that it is a partial penetration weld because we haven't completely gone down the interface. So if this weld were to be flexed, and this could become a high stress point and the crack could start growing over here. Now, if this weld was brittle, then the crack would easily propagate and go through the weld to failure. So one of the most important aspects that we want to understand, in addition to the metallurgy, in addition to the size and shape of the grains and different zones and so on, is the mechanical behavior of the weld, and that we can get by micro-hardness testing. So combination of metallurgical analysis and micro-hardness testing gives a fairly complete picture of the expected behavior of the weld. There are other techniques that can be used, such as SEM and EDAX, to identify different elemental distributions in the weld, but that is not often necessary. So I would say in the majority of the cases, a good cross-section and micro-hardness testing should be sufficient for you to take the first steps in understanding welding quality. The weld section analysis is the soul of welding. It provides a wealth of information. First of all, it tells you the type of bond which is formed, which is not obvious from the strength. A weld can be very, very strong and not have fusion. So this comes as a surprise to a lot of people. The size of the fusion zone and the heat affected zone is obvious from the weld section analysis. So we need to know what the size is, the size of the heat affected zone, which in many cases often decides the material, the weld properties. We can also see internal weld defects, again, which may not be obvious from the weld strength testing. So there might be some fine defects, such as fine cracks or porosities or undercut on the edge of the weld, which may not be very obvious in initial mechanical testing, but will affect the life of the weld. We can also see weld bead alignment, whether the nugget or the heat affected zone is symmetrical or is it biased on one side, and that can tell you issues related to process control. And then, of course, cracks and hardness, which affects the life of the weld. So weld section analysis is a very important first step in understanding your welds, to understand the metallurgy, process, design, and defect-related issues. So if you are new to welding, or in case you haven't done cross-sections before, I would strongly recommend that you get some of the welds cross-section to get a better understanding of what the quality issues are in your weld. Thank you. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking the subscribe button on the bottom right of the screen on your YouTube screen. Videos on specific topics are in the playlist on this channel, so you can review them at your leisure. Looking forward to keeping in touch, and thank you for your time once again.